Hi all, I'm Chongrong Fang. Today I'm going to share our recent work on how to automatically diagnose packet loss issues in the cloud-scale overlay network. This is a joint research work carried out by Zhejiang University and Alibaba Cloud. Tenants can apply for Virtual Private Cloud (VPC) to construct their own private network. It may contain various kinds of virtual devices, such as VMs, SLBs, VFDs, and so on. Here, VFD means the virtual forwarding devices such as vSwitches and vRouters. From the view of tenants, in this inter-VPC scenario, their network packets are transmitted from VM2 to VM7. Actually, the packets in virtual production flows are transmitted from server to server by the underlying physical network. Inside the server, VFDs are responsible for data exchange in the overlay network. The forwarding devices in both networks are important for packet transmission. In the overlay network of cloud computing systems, considering an inter-VPC communication scenario, tenants can configure the virtual forwarding devices, like vSwitches and vRouters, on their own VPC network, such as ACL configurations. Besides, cloud service providers can also configure or update these VFDs. During these actions, both tenants and cloud service providers can lead to packet losses due to VFD faults or non-VFD faults. These packet loss issues can be roughly classified into persistent and transient packet losses. The transient packet losses may not have a visible impact currently, whereas the persistent one will last for a long time and severely harms the profit of tenants or the cloud service provider. Hence, in our consideration, it is more emergent to tackle persistent issues. For other communication scenarios, such as VPC to Internet, intra-VPC communication, VPC to customer data centers, and so on, the reasons leading to packet loss in the overlay network are similar. When a packet loss happens in the overlay network, for example, here is a non-VFD fault on a vRouter. When tenants sense a problem, they will submit diagnostic requests, which include the information of suspected flows. Then the operations engineers of the cloud service provider will use TCP dump to manually check the VFDs traversed by those flows. As a result, for example, engineers reply that vRoute X is dropping packets, but it works well. Maybe tenants should check their configurations. Such reply is not satisfying to tenants. For more detailed information, the network experts will further check and analyze the root cause. Finally, they find that it is due to the misconfiguration of ACLs. Such root cause is useful to quickly troubleshoot network problems. However, the manual diagnosis is time-consuming. In addition, there are hundreds or even more such diagnostic requests every day. Therefore, an automatic diagnostic system is in need. We call it VTrace. For VTrace, our goal are to show the trajectories of targeted packets. Besides, if a packet loss happens, we can quickly locate the culprit VFD and present the root cause. To achieve these goals, there are some requirements for VTrace. First, VTrace should extract the on-site forwarding conditions of packets to reflect the root cause. In addition, VTrace introduces affordable impact on forwarding performance. Furthermore, tenants are not required to help implement VTrace. All these requirements aim at, while implementing VTrace, the impact on tenants' experience should be acceptable. The key challenge of meeting these goals and requirements is how to balance the trade-off between the root cause diagnosis and the low impact on forwarding performance. There is a vast body of prior work related to our research focus. We classify them into three categories. First, for active network monitoring methods, they may not be appropriate for VTrace. since the probing traffic and the production traffic may travel along different paths, which prevents reflecting the on-site forwarding conditions. Then, for passive monitoring methods, they may be require tenants to help collect data. However, we need a non-intrusive way for cloud tenants. At last, network debugging methods perform well in locating the culprit node, but they cannot present the underlying reasons for which a packet is discarded. Our VTrace is designed to fully meet the requirements mentioned before. To automatically diagnose root causes of persistent packet loss, our solution is mainly composed of three essential steps, that is packet tracing, in-depth processing, and path reconstruction. First, for packet tracing and in-depth processing, a naive idea is to mirror packets and send them to dedicated servers or log systems for further analysis. However, such a design lacks a deep check of packets and cannot figure out the on-site forwarding conditions. So, can VFDs perform an in-depth processing for packets? Actually, the forwarding model of VFDs includes the fast path and the slow path. The slow path can be used to process packet in depth. With this VFD's capability, we deploy many debug probes in the VFD slow path to extract the on-site forwarding condition of packets. Here is an example of obtaining a root cause. If packet X is going to be dropped, VFD will check if it is due to an ACL error or a VPC route error or other errors. In this way, the on-site causes will be extracted and recorded in the logs. In production, we have deployed more than 400 debug probes to cover possible packet losses. However, such deep processing is resource extensive for per packet processing. We have conducted a test on a production vSwitch. It can be found that the forwarding rate is down by about 18%, which is not acceptable. We must balance the trade-off between the root cause diagnosis and performance loss. As this work concerns the persistent packet loss, checking a subset of target packets may be enough for the root cause diagnosis. According to our deployment experience, usually checking tens to hundreds of target packets are enough. In this way, the forwarding performance can be efficiently reduced. But how can we realize such flexible tracing and in-depth processing? Here is our design. First, once a VTrace task comes, the controller will install match action rules in VFDs to trace and check target packets. Specifically, for the first hop VFD, the controller tells it the number of packets to be traced with the parameter packet count. Once the target packet comes and the packet count is not reached, VFD will mark the packet through its DHCP value, and then perform the deep check by debug probes. At last, VFD will log the node information and root causes to a local log agent. The log includes necessary metrics such as 5-tuple, root cause, and so on, which are useful for the later path reconstruction. For the following VFDs, they will perform the deep processing for packets with the mark to get on-site causes and then record this information into logs. The actions of the following VFDs are similar. It should be noted that such a design leverages the basic functionality of VFDs and only occupies a small fraction of the flow table resources. With all these logs generated, the next step is to reconstruct the path of packets. A typical solution for path reconstruction is to sort these logs with network topology, which is useful. However, the topology of cloud-scale overlay network is complex and dynamic. Besides, network topology may not be available sometimes. Hence, this solution is sufficient but not necessary. Another solution is to group these logs by packet ID and then sort them by time. But the clocks of different servers are out of synchronization, which hinders us to use this idea. In VTrace, it performs a path reconstruction based on the information contained in the log data. First, the logs are grouped by 5-tuple and the packet ID. Then, they will be sorted in each server. Next, we are going to reconstruct the path for a packet. If the metric mark in the log is equals to 1, it means that it's the ingress of the first VFD. Then it goes to the egress. Next, based on the invariant server information, we find the next hop directly. So are the remaining logs. Finally, the path can be successfully reconstructed, and the procedures for other packets are similar. With such a design, what is the impact on the forwarding performance with VTrace? We conducted several tests on vRouters and vSwitches in terms of the impact on forwarding performance. In these tests, 10 VTrace tasks are issued when VFDs work at the maximum forwarding capabilities, and each VTrace task asks to chase 100 target packets. The setup of both VFDs is the same as the production one. For vRouters, we found that there is almost no drop in the forwarding rate for packets over 256 bytes. And for packets smaller than 128 bytes, there is at most 12% drop in the forwarding rate. This is acceptable for small packets. And the packets in the business traffic usually have a packet size larger than 256 bytes. For vSwitches, we also found that there is at most 1% drop in the forwarding rate only, which means that the impact of VTrace on forwarding performance is acceptable. With respect to the diagnostic time, it costs hours when there is no VTrace system. Now, with VTrace, once a diagnostic request comes, operations engineers can issue a VTrace task to automatically diagnose persistent packet loss issues. After a few minutes in total, a diagnostic result will be clearly presented, namely the problematic VFD and a concrete packet dropping reason. In this way, tenants can get a quick and useful feedback. Next, is VTrace deployable? The answer is yes. We have deployed VTrace in Alibaba Cloud for over 20 months. During the deployment, we get some interesting findings through the usage of VTrace. First, according to this figure, we found that most of diagnostic requests are false positives. Only a few of them do have a packet loss issue. Besides, it can be seen that there is a surge in the number of VTrace being called. This is because there are some online shopping carnivals from early September to the end of December, which places severe demands on tenants' ability to cope with the surge in business, especially those related to e-commerce, live video, and so on. Hence, tenants will expand their cloud resources and conduct pressure tests to meet the upcoming huge business. As a result, these tenant-related operations inevitably lead to the increase of VTrace tasks and packet loss issues. Another finding is that non-VF defaults are usually more common than VF defaults. This is because that VF defaults can be well avoided through software tests before deployment. Further, We collect root causes for non-VF defaults and then classify them into 5 types. The proportion of each type is provided. Interestingly, it can be seen that V-switches are more error-prone than V-routers. And we also found that the causes like tenant security policy blocking and tenant configuration error are the major reasons for packet losses. Also, there are still unknown causes, which indicates that the necessity of maintaining and updating the repository of debug probes. The takeaways of this work is that VTrace demonstrates the effectiveness of the coloring, matching, and logging idea in automatically diagnosing persistent packet loss issues. It also addresses the challenges brought by the cloud scale. Now, VTrace has been deployed in Alibaba Cloud, which includes more than 30 large data centers, and has been used for more than 10,000 times, and successfully served thousands of tenants. In the future, we are going to diagnose transient packet loss in the overlay network. In addition, the integration of troubleshooting the packet jobs in both physical network and virtual network is also an interesting and important program. So,